Okay, this is a solution for the mock for applications of calculus. First problem is an optimization problem, not allowed to use the calculator. A farmer wishes to create a rectangular enclosure ABCD of area 135 meters squared as shown below. The fencing used for side AB costs $7 per meter. So this side costs $7 a meter. The fencing for the other three sides costs $3 a meter. And the farmer creates an enclosure so that the cost is minimum. Find this minimum cost. Okay, so I think it would help if we named some of these sides with variables. So let's say that the CD and AB are X, and CB and DA are Y. We're going to make two equations because whenever you do these optimization problems, you need two equations. Usually one is like an area equation, the other one's like a perimeter equation. One of them is going to be a constraint equation, meaning it only has two variables. The other equation is going to be the main equation, which is going to have three variables. And then you use the constraint equation to eliminate one of the three variables in the main equation, and then that is what you're going to optimize. Okay, so let's see. I'm going to write an equation for perimeter and an equation for area. The area equation is easier, so I'm just going to go ahead and do that first. The area is equal to X times Y. Okay. And the perimeter equation in this case isn't really a perimeter because we're going to do something with these costs of fence per meter, right? So actually the perimeter equation in this case is like a cost equation. So the cost in this case is going to be equal to 7 times X meters plus 3 times X meters plus 3 times Y meters plus 3 times Y meters. So all I did was I multiplied the cost per meter of each side times the length of each side, and I added them all up, and that gives me the total cost. Okay, now we're on the way to solving this problem. We have two equations. One of them is the constraint equation, although at this point, both of them have three variables. The first one has A, X, and Y. The second one has C, X, and Y. But we still haven't used the fact that the area that the farmer wants is 135 meters squared. And we can just plug that in. And then the area equation only has two variables in it now. So that makes it the constraint equation. What do you do with the constraint equation? You solve for one of the variables, and that allows you to substitute in the new expression to get rid of that variable from the other one. So like in this case, I solve for Y. Now I can replace all the occurrences of Y in the other equation with this, and then I can have an optimization equation, a main equation, with only two variables in it also. So I'm just going to simplify this first. So I'm going to put 7x plus 3y is 10x, and 3y plus 3y is 6y. And then I'm going to substitute in y equals 135 divided by x in for y. And now I can have just c equals 10x plus 6 times 135 divided by x. So I substituted in for y 135 divided by x, right? And then now I have an equation with only c and x as my main equation. And I'm just going to simplify this by multiplying out the 6 times 135. Remember, we're not allowed to use the calculator, so I'm going to have to do this manually. 6 times 135 is, let's see, $810. Okay. And this is an optimization problem. What we want to do is we want to minimize the cost. Remember that the way we find minimum points without a calculator, if we had a calculator, we could just do second calc min. we need to take a derivative since we don't have a calculator. So we're going to take the derivative of this expression. I'm just going to rewrite 810 divided by x as 810 times x to the negative 1. And that'll make it easier to take the derivative. So the derivative of c, I'm going to put dc dx to show I'm taking the derivative with respect to x, is going to be 10 minus 810 x to the negative 2, right? Because the negative 1 comes down, so it makes the 810 coefficient negative. Then I set that equal to 0, because the way I find the minimum point is I set the derivative equal to 0. And so now I can subtract 810x squared to the other side. And, x to the negative 2, right? And now I can multiply both sides by x squared so that the x to the negative 2 is not in the denominator anymore. So then I end up with 10x squared equals 810. Now I could divide both sides by 10 because I have an extra z. I have 810 and I have 10. So if I divide both sides by 10, I'll get x squared equals 81. And now we can see that it is indeed a no calculator problem because the square root of 81 is, of course, 9. It could be plus 9 or it could be minus 9. It could be negative 9, but in this particular case, does it make sense to have a negative 9 length? No, so we stick with the positive 9. So now we know that the solution involves a x length of 9. And we can figure out the y length because we have an equation which gets the y value from the x value. So we could say that y is equal to 135 divided by 9. And let's see, that would be equal to, if I put 9 into 13, it goes in 1 time. I subtract, I get 4. 9 into 45 goes 5 times. So the y value is 15. And then finally, the cost is what we want. So we could figure out the cost by just putting in the values that we had. I think it's easier if we just take the original cost equation there. So the cost is equal to 10x, and remember x is 9, and 6y, and remember y is 15. So that would be 90 plus, and 6 times 15 is also 90. So the cost, the minimum cost is going to be 180. So our answer is 180. Okay. Next page, number 2, calculator allowed. Okay, so starting with problem 2, the rest of these problems you can use the calculator on, and you should use the calculator whenever possible because that is how the problems are designed. That's how you're going to have to solve the problems in order to finish it doing 1 mark per minute, which is the pace you need to finish the IB exam. So the following diagram shows part of the graph of a function f of x equals 2x squared. That's, of course, this parabola here. The line t is a tangent to the graph of f at x equals 1, so that would be this straight line here. Obviously, we're going to have to find this area here that's shaded, but before we do that, they're going to ask us a bunch of preparation questions. First, they say, show that the equation of t is y equals 4x minus 2. I put this as optional because it's not really related in particular to this unit, so and it's worth quite a bit of points because it's not... it's a multi-step process, right? Okay, remember that t is the tangent line. And remember, to find the equation for a tangent line, the easiest way to do it is to use point-slope form. So what we need to do is we need to fill in x1, y1, which is a point on the tangent line, and we need to fill in the slope value of the tangent line. Remember, the tangent line has the slope of the curve at this point. The curve itself is 2x squared. The slope of the curve is the derivative, so we could find the m value by first finding the derivative of 2x squared. So we could say y dash, or f dash is 4x, right? Because if we take the derivative of 2x squared, we get 4x. And if we if we plug in the x equals 1 value here, then we find out that the slope at that particular point is 4. So we know that the m value is 4. And we also know that this point here, we know that it is a point on the tangent line. So why don't we use that for our x1, y1? So the x1 value is going to be x equals 1. The y value is going to be the value of the function at f of 1. So if we find out what f of 1 is, that'll tell us the y coordinate there. F, of course, is 2x squared, so f of 1 would be 1 squared, which is equal to 2. So our y value, our y1 value is 2, right? So we found the equation of this tangent line by finding the slope at this point. The slope at this point is equal to the derivative with 1 plugged in, which would give us 4 times 1, or 4. And then we can also find the x and y coordinate of this point by saying, okay, the x value is 1, of course. The y value we get by plugging it into the f function, which gives us 2. Okay? And then the final step would be to arrange it into slope-intercept form. We just need to distribute the 4 and then add 2 to both sides. And that gives us y equals 4x minus 2. And that's what we wanted to prove. Okay, notice how they were able to, even on a calculator problem, force you to do algebra by giving you the answer and asking you to show that, which the only way to do that is with algebra. You can't do that with a calculator. If they didn't say that, you could actually use the calculator function to just find the equation of that line. Find the x-intercept of t. Okay, so this we could do with the calculator. So I'm just going to put 4x minus 2 in the calculator. And then I'm going to graph it. And then I'm going to do the x-intercept function, which is to do second calc 0. Second calc 0, which is option 2. And then I say, I'm going to go slightly to the left of the x-intercept, and then I'm going to go slightly to the right of the x-intercept, and then I hit enter, and the answer is 5, 0. I'm sorry, 0.5, 0. Okay. The shaded region R is enclosed by the graph of f, the line t, and the x-axis. We can kind of see that, right? So the top is bounded by f, the right side is bounded by t, and the bottom is bounded by the x-axis. Write down an expression for the area of R. Okay, so we're going to do an integral to find this area, but you can see that we're going to have to chop this area into 2 sections because if we tried to figure out the area of this and this in between these two, you can see that that only works up to here, and then to the right there is there's a different curve on the bottom. It's the straight line. So we need to chop this into 2 sections. And there's one other way to do it I'll show you in a second, but first we'll do it this way because it's the most obvious way. So we're going to do the function f minus the x-axis for this section, and then to the right we're going to do the function f minus the t function, and then we're going to add the 2 sections together. So one integral is going to be from 0 to the x-intercept, which is 0.5, and then we're going to do f minus the x-axis, and I'm just going to write that for now, and I'm going to substitute in. Then I'm going to add that to the other section, which would be going from 0.5 to 1. And this is going to be the function f minus the t line, right? Okay, now I'm going to substitute in. So the left part is going to be 0 to 0.5. And the f function is 2x squared. And the x-axis is just 0. So I just put 2x to 1. And then I'm going to put 2x squared. And then I'm going to subtract the t line, which is 4x minus 2. And that is my my integration expression. So now what I'm going to do is I'm going to just calculate the area of R using the calculator, because this is a calculator test, so there's no reason not to just go ahead and type this in the calculator. The most straightforward way is using the math button. Oops, let's get out of here, second quit. I'm going to do the math button, and then I'm going to go down to number 9. And I'm just going to plug in exactly what I have here. I'm going to integrate from 0 to 0.5. I'm going to put 2x squared, and I'm going to integrate from 0 to 0.5, 2x squared, and that's it. And I'm going to put x here. And that'll give me 0.0833. So this is going to be 0.0833. And now let's do this part. So again, do math, and then do number 9. Oops, not that one. Math, number 9. And then I'm going to put 0.5 in the bottom, and then I'm going to put 1 in the top, and then I'm going to put 2x squared minus, and then in parentheses, I'm going to put 4x minus 2. Got to put it in parentheses because you're subtracting the t function. And then I put x here. And that also gives me 0.0833. Weird. And then if I add those two together, if I have 0.0833 times 0.0833, I get 0.167. So the area of the area R is 0.167. The other way you could chop this up is you could say, okay, I'm gonna do the entire parabola. I'm going to ignore that white triangle, and then afterwards I'm going to subtract the white triangle. So what you could do is you could say, oh, I'm going to do from 0 to 1, and I'm going to do f minus the x-axis. X-axis is just 0. And then I'm going to subtract the triangle, which would just be 4x minus 2 from 0.5 to 1. So you see, you could like make two shapes, one superimposed on the other, and subtract the shape out afterwards. But I think that this is the most obvious way to do it. Most of the time, you can always approach a problem this way, so I did it that way. Okay, now let's go to the next page. Number 3. And now you can see that sometimes on paper 2, they're going to give you a problem where you may use the calculator, but it's pretty much impossible to use the calculator. So the following diagram shows the graphs of the displacement, velocity, and acceleration of a moving object as functions of time t. So complete the following table by noting which graph A, B, or C corresponds to each function. They're asking us which of these three is displacement, which is acceleration, which is velocity. And there's a couple ways to look at this. One of the ways to look at it is whenever you we do know, of course, that that displacement, when we take the derivative of displacement, we'll get velocity. And when we take the derivative of velocity, we get acceleration. And remember that whenever you have a polynomial, like for example a cube, when you take the derivative of a cube, it becomes a squared. When you take the derivative of a squared, it becomes an x. So when you see a polynomial get less curvy, you're taking the derivative of it. So the most curvy one is graph A, right? And then the second most curvy one is graph C, and the third most curvy is graph B. So graph A is probably your cubic. Graph B or graph C is your velocity, and graph B is your acceleration. Okay, so that's one way you could figure it out. The other way is you could look to see X-intercepts, how those work, right? So if we look at this, let's see where the X-intercepts are. So if we look at graph B, there's an X-intercept right here, right? So if the X-intercept is 0 for graph B here, this must be correspond to a maximum endpoint on another graph. And you're like, oh yeah, graph C. Graph C has a max here, and it corresponds to this 0. So that must mean that B is the derivative of C, right? Because the max point of C corresponds to the X-intercept of graph B. And the same thing happens with graph A. Graph A has a maximum here. It corresponds to the x-intercept of graph C, which must mean that the derivative of graph A is graph C. So we know that C is the derivative of A, C is the derivative of A, and B is the derivative of C. So it confirms that. So we can write down here that the displacement is A and the acceleration is B, which leaves the velocity, of course, to be C. So those are two ways to do it. Write down the value of x when the velocity is greatest. Okay, so the velocity, of course, is the C graph. When is the C graph at its highest point? Right there, which corresponds to t equals 3. Okay, let's go to the next one. Circle the points on the appropriate curve which, if their positions were known, would allow calculation of the total distance traveled from t equals 0 to t equals 7. Okay, remember, in order to calculate total distance traveled, what we need to know is pretty much, we need to know the displacement every time the direction changes. Okay, so in this particular case, there's two ways to see where the direction changes. If we look at the displacement graph, the direction changes every time the displacement graph literally changes direction. So the direction changes here, and I'm going to do this in a different color. Oh, sorry. Okay, so the direction changes here, and the direction of displacement changes here too, right? So if you know where the displacement changes direction, that will tell you the points that you need the displacement for to calculate the total distance, right? Because, like, let's look at this. If we know that the displacement starts at 0 and then it goes to the negative direction, and then it turns around and then it goes in the positive direction, and then it turns around and goes back in the negative direction. In order to calculate this total distance, we need to know where this point is and where this point is, and those are the 2 points I circled, the extreme points of the displacement, right? The places where they change direction. We also need to know the starting and the ending point. So we need to know the starting point and we need to know the ending point. So the 4 places that we need to know the displacement for in order to find out what the total distance traveled are is the beginning, the end, and the minimum and the maximum. Okay, so we just circled those in blue. Okay. Let's go to the next page. Last page, number 4. Okay, number 4. The displacement s meters at time t is given by s equals 5 cosine 3t plus 7.5t plus 10 for t is greater than or equal to 0. Write down the minimum value of s. Okay. Again, this is a calculator problem, so we immediately go to the calculator. Okay, so you're going to go to y equals, and we're going to type in this function. Instead of t, we're going to type in x, of course, into y1. Okay, and remember, anytime you do a trig function, you need to make sure that the calculator is in radians. Since I just turned on this calculator, I know it's in radians already. So I put 5 cosine 3x, and it'll automatically put parentheses around it, but you just close the parentheses and continue on. 7.5x, I'm replacing the t's with x's, plus 10. And then I just graph it. I'm looking for the minimum value of s, of course, for the domain t is greater than or equal to 0. So you might think, oh, the minimum value of s is way down here, but remember, we only care about t is greater than or equal to 0. So to emphasize that point, maybe we could change the window so that we can see just from t equals 0 or x equals 0. Okay. And then we need to adjust the y values with zoom fit, right? The thing is like totally off the screen. That's why we're not seeing it, okay? So zoom fit is option 0, I think. Yeah, option 0. Okay, interesting graph. So now what I'm going to do is I'm going to find the minimum value of S, which is right there, right? I'm going to use second calc minimum, which is 3. And then obviously it's right there, so I'm going to put the cursor, slightly to the left of the minimum point. And then for the right bound, I put slightly to the right. And then I hit enter. And the minimum point is 0.873. Let me just change the color back to red. 0.873, comma, 12.2. And they want the minimum value of S, not the value of T, so the answer would be 12.2. Okay. Find the acceleration A at time T. Okay, remember the acceleration is the second derivative of the displacement. So the first derivative of the displacement is going to be -5 sine 3t times chain rule of 3. Okay, and then the derivative of 7.5t is 7.5. Derivative of 10 is 0. So if I want to simplify this, it would be -15 sine of 3t plus 7.5. Now I'm going to take the second derivative to get the acceleration expression. So that would be -15 cosine 3t, and then chain rule, it would be multiplied times 3. And the derivative of 7.5 is 0. So this would simplify into -45 cosine 3t. So let me write that here. The acceleration is -45 cosine 3t. And then it says, find the value of t when the maximum value of A first occurs. Let's use the calculator to do that. So we'll put -45 cosine 3x, and we will graph that. Oops. Looks like a sea serpent. Okay, I forgot. I need to adjust the zoom fit, right? Zoom fit is 0. Okay, find the value of t when the maximum value of A first occurs. The first occurrence is right there. Okay, so we're just going to do second calc max, and we're going to find that point. Second calc max. And we just put the left bound slightly to the left of that first hump. I think I could just type in a number, but okay. This is improving my video game skills. Okay. Enter. And then I go slightly to the right of the hump. And I hit enter again. And then I hit guess. And the maximum is 1.047. So the t value is 1.047. This is actually equal to pi over 3. You might have encountered that number before, 1.047. And that kind of makes sense, right? Because like basically one cycle of this, because of the b value of 3, is 2 pi divided by 3, and the middle of 2 pi divided by 3 would be pi over 3. So that's why it's 1.047. But since it's a calculator problem, we don't need to use our unit circle knowledge. We can just graph it and do second calc max. And that's it.